Let me show a few examples that I like to consider. Let's consider the game of baseball, where we have a pitcher on the pitcher's mound. And he's got the ball way back here. And he's going to take a big step forward, and he's going to throw that ball. Notice he exerts a force through a fairly large distance. And that does a lot of work on it. Force through a distance gives me a work. Notice the force and the displacement are both in the same direction. These are to the left, which is what we traditionally call the negative direction, but they're in the same direction. He adds energy to that ball, which means K final is greater than K initial, so delta K is greater than 0 or positive. He's added energy to that ball. And remember I said energy was the ability to do damage. That ball, flying at 90 miles per hour, is much more dangerous than that ball sitting in his hand. By contrast, we come over here to the catcher, who's sitting over here, and he's got his mask on. And he's squatting down, and he's got that big, thick mitt in front of him. When the ball hits here, the displacement is quite a bit smaller. He doesn't have as much room to move his hand. But of course, that means he's going to need a bigger force. Okay. Whatever energy the ball had here, assuming that we haven't lost significant amounts to air resistance, it still has as it comes in here. Which means whatever work the pitcher did on it, the catcher has to do the same work, but in the opposite direction. He has to do the same amount of negative work. But because he has a much smaller delta x to work with, this is going to have to be a much bigger force. Notice the pitcher exerts his force with a bare hand, the catcher exerts his with a very thick padded glove. Why? He must exert a much larger force to take away all that energy in such a short distance. Let me give another example. Oops. Suppose we take a gun. Now the gun, when it fires the bullet, that's an explosion. We know from the previous chapter that that means the bullet and the gun must have equal momenta. However, we know that the bullet is much more dangerous than the gun. Well, they both have the same momentum, they have both experienced the same force for the same change in time. However, the bullet being much lighter has a much larger acceleration. Remember, acceleration is force over mass. It has a much higher acceleration, which means for the same amount of time, it's going to reach a much larger v, and with a larger v for the same amount of time, a much larger delta x. That means the work done on the bullet equal to force times distance will be much greater than the work done on the gun. That means the change in kinetic energy for the bullet will be much larger than the change in kinetic energy of the gun. Since they both started at rest, the bullet will pick up more total kinetic energy. Another way to see that, the gun's kinetic energy is 1/2 mass of the gun, velocity of the gun squared, and the bullet's kinetic energy is 1/2 mass of the bullet, velocity of the bullet squared. Notice the bullet is going to be much faster and therefore have more kinetic energy even though it has a smaller mass. Let me take another look here. Let's shrink this. Another way to see this is we can consider the momentum is equal to mv. So v is momentum over mass. So the kinetic energy equal to 1/2 mv squared is also equal to p squared over 2m. For the same momentum, the gun with a bigger mass will have less kinetic energy, whereas the bullet with a smaller mass will have more kinetic energy.